In topic 8, we're going to be talking about a quadratic function. This is different than linear, and the shape in general is much like a U. You can see an example over here in our vocabulary. A quadratic function is oftentimes graphed, and we call it a parabola. So you might see these two terms where a quadratic is the shape of a parabola. A parabola or quadratic function will look like this U shape at different places on the graph. The parent function of the quadratic is the basic one that we compare to. So that parent function is the function x squared. We use this notation, kind of a fancy math notation, to talk about the function f as it relates to x. Now we'll use this function notation. We know that the graph of x squared, kind of gave you a hint here, it looks like this, but sometimes it's important to remember that a function is made up of a set of inputs where I'm going to put in these different x values into this equation wherever I see the letter x. So for example, when I want to put negative 2 in to x squared, I would take negative 2 and square it. A negative 2 times a negative 2 is 4. And then I would plot that on my graph where negative 2 is for x and positive 4 is for y. We'd repeat this process with each of these x values. Now they just gave us a random set of x values. You could pick any of them, but a negative 1 times a negative 1 is a positive 1. The output of 1 helps us graph the xy coordinate. Now you may need to pause the video as I have filled out the table and continued plotting those points on the graph to complete my parent function x squared. This picture over here of x squared will be something important that you'll refer to this entire chapter. So we will talk about some key features of it. The parabola will open upwards. Notice how it's like a cup and it's opening up. It's going up here forever. The axis of symmetry is the line in which we would cut right down the middle to split the parabola in half. So if I were to do that here, cut right down here, we talk about what x value I cut down. And so we would say our axis of symmetry is at x equals 0. I'm going to jump ahead here and note that they say the axis of symmetry cuts through the vertex and divides the parabola in half. So axis of symmetry cuts something in half, and we give what x value that's happening. Notice when it goes all the way down through here, it hits the graph itself at the point 0, 0. That big vocabulary word is vertex. So these two key points here, or keywords, are new vocabulary, but pretty easy to find once you understand what they are. Vertex is the turning point, and the axis of symmetry is the line that cuts it right down the middle. Now, some parts of a graph that we're going to talk about are when a graph is positive or negative. Positive means when the graph is above the x-axis. So positive would be when the graph here is above the x-axis. I like to think of the x-axis as the ground, and the positive ones are the grass that shows through. Negative would be when the graph is below the x-axis or having negative y values. We don't have any on this graph per se, but we'll see some more here on the next screen. So while the graph of f of x equaling x squared is our parent graph, we have a lot of different parabolas that we could look at. And so I'm going to look at this one here and talk about those key features again. So let's start with the vertex. The vertex is that turnaround point. Now, not every turnaround has to be at the bottom. You could have a parabola that opens up down and your vertex would be at the top. We call this top part a max sometimes, and we call this bottom vertex, if it's at the bottom, a min. So our vertex here, we would say, is at negative 1, negative 9. Some other key points we didn't mention on the regular x squared, but be your y-intercept and x-intercept. You know those from previous lessons. The y-intercept, where it crosses the y-axis, is at a negative 8, so we would write 0, negative 8. Our x-intercepts here crossing the x-axis, we have 2 of them, are at negative 4, 0 and 2, 0. Our parent graph, remember, only touched down here at 0, 0, so we would actually have the x-intercept and the y-intercept both being 0, 0. The axis of symmetry, the line that would cut the parabola in half, would be here, and we can draw it easily, but it's important to write it as x equals negative 1. When is the graph positive? This is where I like to think of it as where is the grass growing above the x-axis. So we would have here, we could shade it for positive, But now we need to talk about how you might mathematically tell someone where you shaded. So we're going to write it as from where x is less than -4 and x is greater than 2. Our x-intercepts are our cutoffs where the grass is growing, but we want to tell them all the x values after 2. Anything you plug in will have a positive y value, and before -4. Now, of course, when is the graph negative? We could easily color that, but we have to practice using our math notation to tell someone when it's negative. So we would say in this case that it's negative between -4 and 2. And this says x is less than 2, but x is greater than -4. The last new terminology that we need to look at is when is the graph increasing? Now this has to do with the slope. So it means it's kind of going up or up to the right. It can also be if you had a parabola that's going upside down, this would be where it's going up. Think of drawing from left to right. If I start on this parabola, I'm first drawing downwards and then upwards. So the upwards loops, if you're going from left to right, are where it's increasing. Now, you might be able to say here, I'll circle this in blue, that this right side of the parabola is where the graph is increasing. And that's easy to note on a coloring page or to show us, but we need to turn that into math speak. So we would say it's increasing from the time it turns around here, and we want to use those x values again. So when x is greater than -1, that's because our parabola turns around here when x is -1, so it's always increasing afterwards. When is it decreasing? Well, we could say it's decreasing over here on the left side of the parabola. And that's great that we know that, but we would say that's when x is less than -1. Before the turnaround, it's decreasing. You'll want to practice all these key features and be able to find them, not only on the graph, but to write them mathematically. The last thing we'll look at is what happens when you change our parent function. So here's our parent function x squared, and it's graphed in red, kind of tucked in there. When you have an x squared, there's no number in front of it. We would assume that there's a 1 there because we have 1x squared. I like to think of it as your function x squared has a vertex at 0, and if there's a 1 in front of it, it goes over 1, up 1. So I would have over 1, and it's kind of hard to find. This one goes with the red graph. So over 1 unit, notice we're counting by 2s. That's kind of confusing here, or halves. We go over 1, up 1. That's what our parent graph does. But if you put a number in front, like a 4, for example, look at our blue graph there. Notice that instead of going just over 1 and up 1, it goes over 1, up 4. That's where this dot is. So that coefficient or number in the front of the x squared kind of tells you how much the first step over slopes up. So I would start at 0, 0, go over 1, and up 4 to graph this. Now, being that a parabola is symmetrical, you know you could also go left 1 and up 4. Take a look at the point 5. That would be half as tall. So I will go over 1, up a half, and that's what this dot is. Okay, and it widens the graph, if you will. So a fractional number will definitely widen your parabola, whereas a number bigger than 1, like 4 or 7, will actually narrow your graph. It kind of shrinks in, gets skinnier, if you will. Another thing to note here, we have a -2x squared. Whenever you put a negative, it will flip your function from being up to being down. That's why it's going down. The 2 tells us how much it's going to go down. So over 1, down 2. That a value tells you not only which direction, positive opens up, negative opens down, but also how much to move when you move 1 step over from your vertex. Over 1, down 2.